All right, kiddos, today we're going to talk a little bit about aromatic reactions. Really, we're going to talk mainly about the mechanism, the main way that we want these aromatic reactions to occur. Apologize for the voice, I'm losing a little bit, so just hope that the audio is clear enough that you can tell what's going on. So remember that when we talk about aromatics, we're talking about a very resonant structure. Okay, so if we went back and drew our basic structure of a benzene ring, okay, then what we've got is, a hexagon, and that barely looks like a hexagon. We've got our double bonds here, but that we have multiples, or a couple of different ways that we can show this, right, because it's a resonant structure. Remember that really no one of these actually represents what this looks like, that it's some sort of a blend of these things in between, okay? So instead of it being like, double bonds alternating positions, that it's really like there's 1.5 bonds shared around the entire ring. Those pi bonds are taking up the whole ring. So what this means for us in terms of reactions is that the benzene, okay, the real ring is more stable than either of these two calculi structures here with the double bonds. And that's pretty important to us. That's going to lead into something called resonance energy. And the resonance energy basically says that the actual molecule is more stable than what either of the structures that we would draw are. Now, what does that mean for us in terms of reactions? Well, what it means for us, and the whole thing that we're going to talk about today when we talk about our mechanism, is that aromatic compounds want to react so that they can keep their aromaticity. They want to keep their aromatic structure. They can, during the process of the reaction, one of the double bonds, or they might break the resonant structure of the ring, but they're going to react in such a way that resonant structure will come back at some point during the reaction. So by the end phase, you're going to be back to an aromatic ring. Okay, so that's pretty important for us to remember. So this is the sort of the general process for the main reaction that we're going to worry about pretty much all the way through aromatic reactions, and that's electrophilic aromatic substitutions. Okay, sounds complicated, but we've already done electrophilic. Okay, we're making electrophiles, things that really crave electrons, things that really want to attack, say, a double bond, like in the case of alkenes, and obviously in aromatic compounds we have electron-rich region here in the ring, and so the electrophiles are going to attack that. Aromatic, obviously referring to the ring. And substitution, so again, this is a little different than what we talked about in alkenes. In alkenes, it was pretty much addition, okay? And in the case of aromatics, it's going to be an actual substitution. Essentially what we're going to do is we're going to replace a hydrogen that's on the ring with the electrophile. Okay, so that's the essential gist behind what we're doing in electrophilic aromatic substitution. And we're just going to call that EAS for the rest of the time, because I don't know that my voice can say electrophilic aromatic substitution 100 times during the video. So anyway, aromatic ring, we're going to add to it, in this case, chlorine. We're going to need a catalyst to make that happen, and you'll see why when we talk about the mechanism here in just a second. And we're going to put that chlorine on there. Now, it may look like this is addition, but to know that this is not addition, we sort of need to think about what is the actual structure of that benzene. Okay, and so if we draw our hexagon, I'm sorry I'm drawing so many hexagons because obviously I'm terrible at it. Remember that what's actually going on is we've got hydrogens at each of the points, right? One of them, our formula for benzene, of course, is C6H6. And so each vertex on the hexagon has a hydrogen on it. And so what we're doing when we put this chlorine down here is that we're essentially pulling one of the hydrogens off, and the chlorine is going to take its place. Okay? So as we talked about with excuse me, with alkanes and with alkene reactions, the real heart of this is how does this actually happen? Not just that it does happen and that this is our product, but how do we get there? Okay, so we're going to talk a little bit about the mechanism of the EAS. And so the mechanism for EAS, we're pretty much always going to require some sort of catalyst. The point behind the catalyst is to help us get our electrophile. Okay, we're doing electrophilic substitution, so we're going to need a strong electrophile to make that happen. So when we put these two things in here in this chlorination reaction, our chlorine is actually a relatively weak electrophile. It's got a ton of electrons, so we're going to need a catalyst to essentially turn this from the weak electrophile that it is. Now it's electrophile, but it's weak. We're going to need to turn it into a much stronger electrophile. And so this process works like this, okay? The iron 3 chloride is essentially going to come up next to this chlorine. We're going to form what it shows here, sort of like partial or forming bonds, okay? And as that happens, when the FeCl3 moves close to this chlorine molecule, it's going to start to polarize it, and it's going to start to pull the negative end here. It's going to start to pull this chlorine off over to itself. It's going to get a slight negative charge. And then this other chlorine here on this end is going to start to have a slight positive charge. Well, as we start to get that slight positive charge, that's going to create a really strong electrophile. So that then, this chlorine here, okay, is what is going to basically attack the ring and going to cause us to replace our hydrogen with itself, okay? So step one is creation of a strong electrophile. We have to have that step in order to make this process work. So what happens then? Well, the next step is we're going to add it to our benzene ring, okay? So here's our benzene. Here's what we have in the previous process. Here we've got our FeCl3. The chlorine, it's going to start to work on the chlorine. It's basically going to start to split this bond here, okay? And what's going to happen is that this chlorine here, okay, is actually going to join to the FeCl, okay? So we're going to get FeCl4 minus, okay? So that's one of our intermediates. And then the real important intermediate that we're talking about is that we're going to add a chlorine on here. We're going to break the double bond here, okay? And we're going to add a chlorine. So if we were talking about this in terms of what is going on with the electrons, okay, let me erase some of the stuff that I've got here. If we're talking about that in terms of what's going on with the electrons, well, we're going to get this, okay? We're going to form a bond here. Now, what you may be saying to yourself is, well, if I take both of the electrons from this bond, then that's going to sort of leave this chlorine short, and the answer to that is essentially yes. That's exactly what's going to occur. Okay, we're going to break this double bond, and we're going to form a bond with this chlorine. Okay, now, when that happens, the first thing that you should note is that we get our good friend, the carbocation here. Okay, so we're going to get a carbocation that's going to form at the other end of the bond. So one end of the bond, the Cl is going to hit. At the other end is where we're going to get our carbocation. Think back to your alkene reactions, Markovnikov's rule, and all that stuff. The electrophile attacks at one point, we get a carbocation at the other point of that double bond. That's exactly what's going to happen here. Now, since this is a resonant structure, or at least was before we broke that double bond, that means that that positive charge can get shifted around, okay? So the double bonds can shift, and again, not really a case where they're shifting, more a case of there's a break in the ring where the electrons were, and so we get a little bit of a positive charge there. So the way we're going to draw it, represented, of course, in resonant structures, though, is that, hey, I'm going to move my electrons around, and more to the point, I'm going to move where my carbocation goes. It's going to shift it into our ortho and para positions compared to where we originally were. Okay, so at this point, what we want is we want to find some way to restore the aromaticity of the ring, okay? Ordinarily, if we're talking about alkenes, once our carbocation formed, then we would have something come in and join there in our case of our addition reactions. But remember, this isn't an addition. This is a substitution. And my goal here is that we're replacing this hydrogen that was originally on the ring with a chlorine, okay? And so we're substituting. We're not just adding additional things on by breaking the double bond. And the reason for that, of course, is that the benzene ring itself, with all of its aromaticity and the delocalized pi bonds around the ring, is more stable than this cyclic diene is, okay? And so we want to get back to that aromatic state. So instead of adding something here, what we're going to try to do is to restore the double bond, okay? So here's the way that that is essentially going to work, is that we're going to take our bond that was here, our two electrons here, and they're essentially going to come back into the ring. And so we're going to get the restoration of our double bond there. When that happens, if the bond goes there, okay, from where the hydrogen was, then the hydrogen essentially is going to get removed at this point. It's going to add to a chloride ion, and that is going to give us our other substituent. Okay, that's going to give us That's going to give us our other product, which would be an HCl in this case. Now, of course, those among you who are real super picky about this, you would say, okay, well, there's something else that comes back too, right? I get the restoration of my catalyst, and so that is back as well. And so what is going on here is I'm restoring the aromaticity of the ring. I'm now back to a benzene ring, to an aromatic ring. And this proton, remember that's essentially all that this H is because it's an H plus at this point. This proton is going to go away and it's going to bond with the chloride ion. Remember, if it's a chloride ion, it has 8 valence electrons. So essentially it is donating the full bond there to form the HCl, okay, coordinate covalent bond sort of thing. Okay, so that's the steps of our EAS. And so just to generalize the whole thing, we've got a benzene ring. We have to form a strong electrophile. Okay, so usually that means one of our reactants combines with the catalyst to form a strong electrophile. That strong electrophile is going to attack a point of the ring and attach. That's going to create a carbocation situation. Remember when you see these dashed lines here, that essentially means that the double bonds could be anywhere in that part, and therefore obviously we could alter where our carbocation goes. And then what's going to happen is that hydrogen is going to get pulled off, okay, by getting attacked by a negative ion. So it's going to get this proton here, which is essentially what this is going to get attacked. The bond that was holding on the hydrogen to the ring goes back into the ring. Those 2 electrons come back in, and so that allows us to restore the aromaticity of the ring, which is the more stable state. All right, hopefully that helps you to know the general process. In our next video, we're going to just essentially show some more examples of ways that EAS gets used, more reactions that we're going to actually substitute stuff onto an aromatic ring.